Hello everyone. The explicit dynamics analysis enables us to capture the physics of short duration events that undergo highly nonlinear transient dynamic forces. The common application of this analysis includes a simple study of a baseball impact when it hits the bat to a complex vehicle crash. Hence, it is crucial to obtain accurate results. In implicit analysis, the convergence is based upon force, moment, displacement, heat, etc. to ensure the equilibrium. However, the numerical formulations in the solver for explicit dynamics analysis only account for the mass and momentum conservation, but not for energy conservation. Thus, to make sure the simulations predict accurate results, the explicit solver always takes the total energy balance to monitor energy conservation. In this video, we will see what energy balance in explicit dynamics is, the main causes of energy imbalance, and how to remedy them. Ready? Let's get started. During the explicit dynamic simulation, the total energy of the system should always be conserved. As per the law of conservation of energy, it can neither be created nor destroyed, and it can be only converted from one form of energy to another form. To simplify it, a system should always have the same amount of energy, unless the energy is either added from or lost to the outside. This equation explains the total amount of energy in any system. Here, UT is total internal energy, UI is initial internal energy, W is work done by or on the system, and Q is heat added to or removed from the system. Let us consider some examples to understand this. In the drop test of a beverage can here, the can is dropped from a certain height. When it reaches the ground, the kinetic energy is the maximum. When the impact happens, the kinetic energy is absorbed by the can and it is stored as strain energy, also called internal energy here. And when the can bounces back, the internal energy is converted back to kinetic energy. In this second example of the Taylor impact test, due to the collision of the cylinder, the kinetic energy converts to internal energy, leading to deformation. Similarly, in the brake analysis, the kinetic energy gets converted to thermal energy due to friction. Thus, we should be checking the energy balance while performing the explicit dynamic simulation. That means comparing the current energy of the system at a given point with the initial reference energy. For example, it can be checked using an energy error term. Here, the energy error is defined as the ratio between the relative energy to the maximum energy value between current energy, reference energy, and kinetic energy. Here, the reference energy is the sum of internal energy, kinetic energy, and hourglass energy at the beginning cycle. The current energy is the sum of internal energy, kinetic energy, and hourglass energy at the current cycle. And the work done is the sum of work done by constraints, loads, body forces, contact penalty forces, and energy removed from the system by element erosion. Another possible way to confirm the perfect energy balance is by checking the total energy. If the total energy, which means the sum of the initial total energy and external work, is equal to 1, it can be checked using the energy ratio, which can be defined as the ratio between the total energy to the sum of initial total energy and external work, and it should be equal to 1 for the perfect energy balance. However, while solving the explicit dynamics problem, there can be different sources that cause energy imbalance. Let us discuss some of them and see how they affect the overall analysis. The first source is the hourglass energy. This type of energy imbalance is caused by the hourglass modes, which are non-physical, zero energy modes of deformation, and they produce zero strain and no stress. For the quadrilateral and hexahedral elements, the calculation of strain rates is based on the differences in the velocity of the diagonal components of the elements. If these elements distort in such a way that the differences in the diagonal components remain unchanged, these elements will have zero strain even if the elements have distorted. Such mesh distortion is called hourglass deformation. The hourglass deformation could be introduced by erroneous material property data, a coarse mesh, loading that is localized to a node or edge, and even the choice of element formulation. For avoiding hourglass energy, we can refine the mesh and verify the material property data. Or we can also introduce hourglass damping that is added to the nodal forces at each corner of quadrilateral and hexahedral elements to resist such form of element distortion. The second source can be due to erosion. A Lagrange element in explicit dynamic simulation could distort severely under extreme external loading. When the distorted Lagrange elements are eroded from the simulations when they meet the predefined criteria, the mass in these elements is also removed from the calculation. Hence, the energy stored in that mass loss is also lost. So, the total internal energy decreases as the distorted elements erode. This can cause an energy imbalance. During the erosion process, it removes the cells from the calculation. So it is typically not representative of the physical process, but rather a method we use to prevent the time step from getting too small. The rule of thumb is to set the erosion criteria such that it should not affect the results. It is numerical technique for solver to carry on. The next source can be the boundary conditions applied to the system. If during the explicit dynamic simulations there is an energy increase due to work done by external forces, for example displacement, boundary condition, gravity or acceleration, or adding new parts or new materials, the current energy may exceed the reference energy, and thus it is possible for the solution to have energy imbalance. Another example is when we use the boundary conditions to model an infinite boundary so that a traveling shock wave will not reflect at the boundary of the computational domain and thus does not interfere with the numerical calculation. These boundary conditions allow the shock wave to exit the computational domain without reflection. Thus, the internal and kinetic energies carried by the shock wave exit the domain as well. This reduces the current energy and may increase the energy imbalance in the system. One more source of energy imbalance can be observed during the detonation and expansion of energetic materials such as explosives. In the simulations involving Euler solvers, the cause can be a low mesh density that has been used for the area where high internal energy such as an explosive is present. When the mesh is coarse, the numerical error in calculating the total internal energy is increased during runtime. This could reduce the current energy and could cause an energy imbalance. The user could refine the coarse mesh to reduce the energy imbalance. Now let us understand how we can handle the energy imbalance in the system. As discussed earlier, we can check the energy imbalance differently in different products. If it can be explained and we know where the energy comes from and where it goes, it should be fine. The energy imbalance does not mean that the results are completely wrong. For any product, while performing explicit dynamics analysis, usually the user only needs to pay attention to the energy balance and if there is a spike in the energy history chart. If the energy imbalance gradually increases, usually the results can be fine. But if the energy imbalance goes up very quickly in very few cycles, the user needs to examine the results and the model setup very carefully since it usually indicates the problems with the model setup or the solutions. So in this video, we have talked about energy conservation and it is important in explicit dynamics to check energy balance. Various reasons can lead to energy imbalance. We need to check them carefully. The results may still be reliable even with the presence of energy imbalance. I hope you have found this video informative. Thank you for watching and do check out our other courses to discover more useful learning resources.